Welcome students to Unit 12, Organic Chemistry. This is our final unit in chemistry. We will not be going very deep into organic chemistry as it is a full year-long course in college. We will instead just be doing a brief overview, basically only the material you have to know for the SOL. As such, there is only one subunit for this, and it is organic chemistry. Organic compounds are carbon-based compounds because carbon has the unique ability to form covalent bonds with 4 other atoms, including itself, and because it can do so, it can form long chains of carbon-based compounds. Those compounds can be complex, long chains, or cages, or folded molecules. We will stick to simple chains and only briefly discuss aromatic or ring structures. So again, organic compounds are carbon-based. There are exceptions, however. Carbon oxides, so compounds composed exclusively of carbon and oxygen, are not considered organic. They are inorganic compounds. Compounds in which carbon is an anion, so carbides, are also excluded. And the carbonate anion, being that that anion is made exclusively out of carbons and oxygens, it is excluded. A general rule of thumb, and by no means 1000% accurate, is that an organic compound contains carbon and some number of hydrogen. So a generality would be that organic compounds are compounds formed from carbon and hydrogen, as well as a large number of other things. So we will focus in this course exclusively on hydrocarbons, which is the simplest of organic compounds, again composed exclusively of carbons and hydrogens that form long chains. We distinguish these different hydrocarbons based on how the carbons are bound to one another. As organic chemistry is the study of carbon-based compounds, they have their own nomenclature. We name organic compounds using the same prefixes we've learned so far, where deca means 10, nona means 9, octa means 8, hepta means 7, hexa is 6, penta is 5, but then things become different. From 4 backwards, 4 is usually tetra. However, we start using a different prefix system where 4 is bute. 3 would normally be tri, but 3 in organic chemistry is prop. 2 is usually di, but 2 in organic chemistry is eth. And a single carbon we would say is meth, rather than mono. You can remember that these first 4 are different by the phrase me eat peanut butter, because peanut butter is an organic compound. So again, we use these prefixes to denote the number of carbons in the longest chain. Find example 1 in your packet, and we will name the longest chain using the prefixes. So for this first chain, we have 1, 2, 3, 4, 5, 6 carbons. So we would start this name by saying hex. In example B, we have 1, 2, 3, 4 carbons. So we would start this name with bute. In example C, we have 1, 2, 3, 4 carbons. So it would also be bute. And in example D, we have this line structure. Each point on that line structure represents a carbon. So here's 1, 2, 3, 4, 5, 6 carbons. So we would start this by saying that it is hex. You'll notice that all 3 of these examples have different ways of denoting the structure of this organic compound. As organic chemistry is a massive subset of chemistry, there are many different ways to represent the same thing. So this first example is what's known as a structural formula, showing the central atom, in this case the carbon, and what it is bound to. Example D is an example of a line formula, which usually uses peaks to denote different carbons. Example B and C are simply different representations of the two. Again, this is far more complicated in reality than this brief overview, but that's good enough to get you through at this point. If all your carbons are held together by single bonds, it is known as an alkane. Alkanes are the simplest of hydrocarbons. They are what are known as saturated hydrocarbons, where every carbon holds the maximum number of hydrogens it can. So, for this example, we have methane, where that carbon is holding all hydrogens and all the hydrogens it possibly can. In this second example, we have butane. All of these carbons are holding the maximum number they can. The ends are holding 3, the ones in the middle are holding 2 hydrogens. The basic formula for an alkane is that whatever number of carbons you have, if you double that and add 2, that's how many hydrogens it has to have. So anything with all single bonds, any organic compound with all single bonds, we will end the name with ane. That first example, all of the carbons are holding the maximum amount they can. The ends each have 3, and the carbons in between are all holding 2 hydrogens. So this is an alkane. So we would call this hexane. Alkanes are often used as fuel. For example, propane is what comes out of your gas grill. Prop means 3, so you would have 3 carbons, and ane means they're all held together with single bonds. Since the only ending is ane, each of those carbons is holding the maximum amount of hydrogen it can. So this end carbon, let's call it carbon number 1, already has 1 bond, so it needs 4, so those other 3 must be hydrogens. This end carbon, carbon number 3, has to have 4 bonds, so 1 to the carbon, and then 3 hydrogens. The carbon in the middle already has 2 bonds, but has to have 4 in order to be at its lowest energy state, so it picks up those 2 hydrogens. So our structural formula for propane would be 3 saturated carbons. Because they are always nonpolar, alkanes tend to have very, very low intermolecular forces and therefore are typically gases and rarely liquids and almost never solids. Alkanes can form straight chains, as we saw before. They can also have branching functional groups. A functional group is where we replace one of the hydrogens with a group of atoms that have different names. These side chains are named just like anything else. So here we have 1 carbon, so we would call this a methyl group. This is also a methyl. Alkanes are also able to form ring structures known as cycloalkanes, where the carbons form a ring of some sort. Aromatic or cycloalkanes do exist. A double bond between your carbons makes an alkene. So alkanes are the simplest, like the letter A is the first letter you learn, so single bonds are an alkane. Alkenes have double bonds. An alkene has 2 E's, and that's how I remember it. Because these carbons do not hold the maximum number of hydrogens they can, they are known as unsaturated. So they get the ending -ene. Anytime we have a double bond, it will end in -ene. So looking at example 1 again, example B and C both contain a double bond, so they would both be butene. However, the location of that double bond does make a difference. So we denote the location of that double bond by saying which carbon it starts from, providing the lowest number carbon possible. So we number our carbons from either the left or the right, and the lowest number possible is what we go for. So for example B, we could number our carbons as they are, or we could number them in the reverse. So our choices are either 4-butene or 1-butene, and you want the lowest number possible. So we would pick 1-butene to say that the double bond occurs at the first carbon. A quick side note here, you could write it with the 1 between where the unsaturated point is. So you could also have but1ene. We usually use only this system when there are a large number of substitutions, where there is a large number of hydrogens that have been removed, and it's not simply one substitution as it is here. So the better answer for this, again, would be 1-butene. In example C, we could number the carbons as they are now, or we could number them 1, 2, 3, 4, like this. So our choices are either 2 or 3, and again, you want the lowest number possible, so we would call this 2-butene. Alkenes are also typically non-polar, and therefore they have very, very low melting and boiling points, as their only intermolecular forces are London dispersion forces, which increases with the number of electrons. So long-chain alkanes tend to be liquids, and short-chain alkanes, which is where we'll focus, tend to be gases. An example of alkanes are ethene. Ethene comes off of fruit, which causes it to ripen. For example, apples produce a large amount of ethene. And limonene, which is the chemical responsible for the lemon scent that you smell. Seen here. Alkenes also tend to be the starting material for polymers, as that double bond tends to attract other electronegative elements towards it. The general formula for an alkene is, if you have a number of carbons, simply double it. If you have a triple bond between your carbons, you have an alkyne. Just like alkanes, A is the simplest letter, so that's a single bond. Alkenes have 2 E's, that's how I remember that. Alkyne has a Y in it, and in order to draw a Y, you need 3 lines. So a triple bond is an alkyne. The simplest formula for an alkyne is the number of carbons doubled minus 2 is how many hydrogens you would need. Again, as these carbons are not holding the maximum number of hydrogens possible, these are considered unsaturated. Back in example 1, problem D is an example of an alkyne. Again, where that triple bond occurs needs to be denoted, so numbering our carbons 1 to 6, our choices are 3 or 4 hexyne, so we would say this is 3 hexyne. Alkynes are often produced from the refining of oil, and again are used in polymer synthesis, the formation of different polymers. Again, when it comes to nomenclature, we name the longest chain present and then note any substitutions for hydrogens. So the simplest substitution would be if there's another chain attached to it. So taking the longest chain can mean that we can wind a little bit. If we look at this example, we have 1, 2, 3, or 3 carbons. In either case, we would say that there are 3 carbons in the longest chain, and that longest chain contains a double bond. So this is propene. That double bond occurs at carbon 1. No matter which way you number this, it has to be that the lowest number is where the substitutions occur. So that lowest number here would be 1 propene. However, we have another substitution present. A chain of carbons comes off of carbon 2. How long of a chain? A single carbon. So we would say it's a methyl group off of carbon 2. So the full name for this organic compound would be 2-methyl-1-propene. Another side note, depending on your level of chemistry, this one is often understood. An acceptable name for this would also be 2-methyl-propene, as it is understood that if not noted, carbon 1 must be where that double bond occurs. Otherwise, you wouldn't note it. So both answers are acceptable. Check with your professor and listen to the lecture in class to ensure what answer you're looking for. My personal students, I will take either answer in all honesty. With that being said, you are now able to do page 6 in your packet. Please pause the video and complete page 6. There are other functional groups besides chains of carbons, and there are a lot of them. In this class, rather than focus on all of them, we will focus on only a select few, those that make an appearance on the SOL or have a functional purpose in your life. Not to say that organic compounds don't have a functional purpose in your life, just for simplicity's sake. Again, the purpose of this video is to supplement the class for the Virginia SOL. Check with your professor to get a complete list of the functional groups you are expected to know. So the first functional group that I would like you to know are halides. Halides are when a halogen takes the place of one of the hydrogens in our chain. Those halides are simply noted by their root name. Ido for iodine, bromo for bromine, chloro for chlorine, and fluoro for fluorine. We simply note where they occur in the longest chain by saying what carbon they are attached to. So for this first example, our longest chain of carbons contains 3 carbons, so we would say this is prop. They're all bound by a single bond, so this is propane. And we have this iodine that comes off of carbon 2. So we would say this is 2-idopropane. In this next example, we have 1, 2, 3, 4, 5 carbons. So we would say this is pent. They're all bound by single bonds, pentane. And we have 2 halide groups that come off of one of the carbons. As it is numbered now, that would mean they were both on carbon 5. But remember, we want substitutions to be on the lowest number possible. So we wouldn't use these numbers, we would label them the other way, making both of these halides come off of carbon 1. So on carbon 1, we have a fluorine and a chlorine. We put them in alphabetical order. So this is 1 chloro, 1 fluoro, a hydroxyl group off of a carbon-based compound is what makes an alcohol. The addition of that hydroxyl group changes the E at the end of our organic compound to an -ol. So here we have 2 carbons, so we would say eth. They're all single bound, we would say ethane, but this hydroxyl group at the end means that this ends in -ol. And again, we would want to know where that substitution is, and as they are labeled now, we would not say it's 2-ethanol. You would put this is carbon 1 and this is carbon 2. So this would be 1-ethanol. But again, that 1 is understood, so we can just call this ethanol. Here we have 1 carbon, so it would be meth. They're all single bound, so be methane. And we have this hydroxyl group, so this becomes methanol, or grain alcohol. The addition of a nitrogen to an organic compound provides a fishy smell. These are amine groups. Amines simply change the E to amine. So here we have 1, 2, 3, 4, 5 carbons. So this is pent, all single bound together. So this would be pentane, but this amine group makes it pentamine. Organic acids are acids that contain a carboxyl group. A carbon double bound to an oxygen and a hydroxyl group. It is this hydrogen that comes off organic acids. When naming organic acids, we simply end them in anoic acid. So here we have 1, 2, 3, 4, 5, 6 carbons. So this would be hex. All single bound together means this would be hexane. We change that ending to anoic acid. So this would be hexanoic acid. With that, you should be able to complete page 10 and 11 using your packet. I did not go over esters, ethers, or ketones. However, use the picture on page 4 in your packet to identify them. The letter R simply denotes more chains that could come off. So an ester is simply a chain of some carbons, a chain of some more carbons, and then between those two chains, you have a double bound carbon, a double bound oxygen to a carbon and an oxygen. So that would be an ester. Again, use page 4 in your packet to complete page 10 and 11. Pause the video now and do so. Lastly, for this tour of organic chemistry, you will need to know about polymers. Polymers are long carbon chains made up of small subunits called monomers. Mono means one, so one piece that comes together to form many, poly means many, pieces. That is what a polymer is. Think of them like Legos. Monomers are those individual Lego pieces that come together to form like the Millennium Falcon. So man-made polymers are all the plastics in your life, like polyethylene or plastic bags, and polyvinyl chloride, or PVC for short, is what gets water to your house. Nylon is another example of a polymer. And most of your pharmaceutical drugs are polymers in some way or another. There are natural polymers in the world, and these are what you learned about in biology. For example, proteins are made up of small amino acids, so amino acids are the monomers of proteins, which are the polymers. Amino acids come together to provide all of the proteins in your body. Carbohydrates are the sugars of your body. Carbohydrates are made up of monosaccharides. Mono means one, saccharide is sugar, so a single sugar, like glucose, comes together to form the carbohydrate glycogen, the fat that holds together your body. Lipids are comprised of fatty acids. So an example of a lipid would be wax. And lastly, nucleic acids are polymers made up of your DNA bases. Adenine, guanine, thymine, and cytosine that you learned about in biology, those are the monomers that come together to form your nucleic acids, DNA, RNA. So with that being said, that is the end of organic chemistry that you have to know for the Virginia SOL. Most likely, I am providing you this lesson just the day before your SOL because it's not a very large section. You will most likely have to be able to tell the difference between a man-made polymer and natural polymers. Simply being able to state which substance is a natural polymer and which substance is a man-made polymer. With that being said, good luck on your SOL.